Welcome to Shop Talk Live, the aluminum series. I'm Andy Weyenberg, and I work in the aftermarket performance and motorsports industry for Miller. And I'm also joined by James.
Evening, everyone. My name is James. I'll be the connection from the chat on YouTube to Andy. So if you have any questions, feel free to ask them here in the chat, or you can always email those questions to us at shoptalklive@millerwelds.com. We do monitor that email address, and we'll get that question answered for you. One small housekeeping item tonight. This will be the last episode of the Shop Talk Live aluminum series. We plan to take a break through the summer, but we'll be back later this year with some more Shop Talk live streams. If you have any suggestions on what you'd like to see covered, please put them here in the chat, or again, you can email us at shoptalklive@millerwelds.com. You can also sign up for email alerts for future Shop Talk Lives or live streams that we might do. I will be putting a link in the chat for that as well. Andy, one of the common questions we get about aluminum and motorsports is, what are some of the common alloys of aluminum that we might see in the motorsports industry?
Yeah, that's perfect. Yeah, we're going to actually discuss the common alloys used in the aftermarket performance industry. We're going to talk about their fabrication characteristics and welding and filler metal choices today. So I would say the most common alloys that we see, they're typical alloys across a lot of industries, but for the motorsports industry, I'd say the most common are going to be like the 6061 alloy, 5052, and 3003. We'll also discuss a little bit later some casting alloys, whether you're working with cylinder heads, cylinder blocks, transmission cases, things like that. So that's also pretty prevalent. So we'll talk about some of those alloys and filler metal selections too. So I guess if I would kick it off, I would start with maybe the 6061 alloy. So it's also commonly called an aircraft grade aluminum. It's highly machinable. It's very strong. But for fabricating, it's not so great to fabricate or bend or form 6061. What happens with it, it's so strong that it actually tends to crack. And I actually have a good example of that. So let me change you over to a different camera. So this is 6061, 1/8 inch thick. And what I did is I bent it at a 90 degree. So, in itself, it's not hard to bend. The bad part is when you do bend it, it cracks. So this is only a 90 degree bend, and it actually cracked to the point where it has fatigued this part so bad that I could literally pull it apart. So it's not very good for forming and using it in a fabrication point where you need to put in a brake, put some bends in it, things like that. It's very hard to put in a bead roll and actually put a decent bead in it. You can still get it in sheets, obviously, and still fabricate parts and pieces and weld it to other weldments. So that part of 6061 is great. For the most part, we see 6061 in machining bungs and fittings, or machining items that don't actually sometimes even need welding. Might be brackets or housings that say maybe your remote oil filter housing would be machined out of 6061, and it might be welded to a bracket that gets bolted to a roll bar or something to that effect. But most of the time you'll see in what we'll be talking about, like on this particular item, this is an expansion tank. It's actually made out of 3003 material, but all the bungs and fittings are that 6061. So we'll talk about the filler metal choices on using 6061. One of the better materials for fabricating, if you're going to be bending it and forming it, it's still really strong, is going to be that 5052 alloy. Now, 5052, it also comes in sheets. You can bend it. It's a little difficult to bend in certain applications, but you can bend it quite easily with standard hand brakes. If you do bend it, you'll notice that the 5052 will bend, and the bend area will still stay structurally sound. The bad part about 50-52 is that if you get to an overbending situation, there is a limit. So now this is 50-52 at 120 degrees. And what you'll see in this case is, if I can get the camera to focus in on it, you'll see some micro cracking starting at the bend area. Now, that micro cracking is only going to get worse. That's probably a better image of it. That micro cracking is going to get worse as you start overbending it. So this is only at 135 degrees, and you're going to start seeing that cracking being more prominent on this. So you're getting to the point now where you're getting to the point where this is going to be structurally compromised. So you may want to think about gusseting or changing that design, maybe to having that be a welded joint instead of just a purely bent or formed. 50-52, you can put, if you have a bead roller, you can still bead roll it, and that does increase the strength. One thing about 50-52, any of those sheets, actually, a lot of times you'll see it when you buy it, it has this plastic film on it. Now, the plastic film might be on one side or it might be on both sides. Now, on this particular piece, it's actually on both sides. So when you peel that stuff off, what you'll notice is the aluminum looks really clean underneath. I mean, that thing looks ready to weld, right? But not really. So that film keeps it protected from getting scratched and stuff, but unfortunately it still does leave a residue on here, and that oxide layer is still pretty heavy on this piece. And I can prove that simply by just taking a little bit of acetone, putting it on a rag, and just you can literally wipe it. Even though that piece looks clean, look at what's coming off of that. Okay, and really it didn't change what the aluminum looked like at all. So you'll want to make sure you clean and prep that aluminum before you weld it, even if it has that film on it. Okay, so that film is only protecting it from getting scratched. It's also great for when I'm fabricating it, because I can make my marks on it and put it in the brake, and it's easier to see. But when it comes time to welding it, you got to take the extra time to clean it. So that's using a dedicated stainless steel brush just for aluminum. If you've seen some of the previous Shop Talk Lives, especially the beginner welding aluminum one, you'll notice they probably covered that quite a lot, is cleaning and prepping the aluminum. So we wire brush it, and then a little acetone on the rag or denatured alcohol also works really well. And clean that oxide dust off of that piece before you weld it. So some example, I guess we could do that too, is talk about annealing. If you have an issue with bending it and you want to anneal the aluminum, you could do that as well. Annealing is just the effect that you're actually softening the aluminum, and you can do that with an acetylene torch or any type of heat source that gets it up to that level where you're removing that higher tensile strength of that aluminum. Now, I use a couple different methods of doing it. I'll take a Sharpie marker and I'll just draw a couple lines where I'm going to be bending it. I don't necessarily anneal the whole sheet. I might anneal just where I'm going to be bending it. So I'll take a Sharpie marker, I'll draw that on there, and then I'll take my torch and I will go along that line until the line disappears, and that's going to be about roughly that temperature level that you need to anneal it so you can bend it easily. Some items that are commonly made out of 50-52, this is a part of a racing seat. So this is 50-52. It's very strong. It has a good memory. So if it does get in some sort of accident, it does pull back to its shape. It has a little bit of give. This particular item also has a 5052 formed piece around it that is welded to keep it in this shape. But racing seats you'll see definitely being made out of 5052 aluminum. Some heat exchangers, radiators. Now this is going to be an area where sometimes both 5052 or 3003 might be used. On this particular one, it's a 5052 on the tanks, and it's actually 3003 on the top and bottom rails. So this is kind of I would say like an alloy mutt. It's got a little bit of everything, including 6061 for your bungs and fittings. So this is a great piece to show the different alloys being used. 5052 is great. I use it for anything that I still need at higher strength. I make these tall wheel stands that I put on our race cars. It gets the car up in the air. That's all made out of 5052. That way I can still get the car up in the air. I can work underneath it, but yet the car is still at its static ride height. So for the most part, all the suspension is in its right geometry. I can put turn plates on it and do all my front end settings, even string the car to make sure everything is square up on those stands. And those stands are made out of 5052. We'll get into the 3003. That's probably the stuff I use the most, just because I can make a lot of tight bends with it. It forms real easy. It bead rolls really easy. So you can add strength by adding bead rolls to it. This is a power steering reservoir that we make for cars and our race cars. This actually, it's a kind of an unusual shape because it actually gets put in the front engine area where the bay bars come down, and it actually fits right inside where the front bay bar comes down and meets the frame. So this tab mounts it to the bar. These tabs here mounted to the frame. Again, the fittings are 6061, but the aluminum alloy for the tank itself is 3003. So this is very easy to make this stuff. That's why I like using it. So I've got some bend examples of 3003. This one is quite impressive because all I did was take the 3003 and I bent it at about 180 degrees, and you can still see that the bend area is not compromised with micro cracking at all. So that is an excellent material to fabricate with. Any questions so far?
Yeah, we've got a couple. One of them specifically, when you're talking about the 5052, one of the questions we got was, does it matter if you bend it with the grain or against the grain?
No, it doesn't matter. You're still going to experience some micro cracking, and it's still tough to even decide which way your grain is going on the 5052. It doesn't, especially with the sheet on it, with the plastic piece on it, you can't tell which way the grain is going. At least I can't. So it's going to crack if you overbend it, and that's the only way to get around that is to increase your bend radius. So if you need to make a more included angle, so on this particular piece, I stayed true to that bend radius by thickness. But if I wanted to make this literally 135 or more degrees, I could increase the bend radius there, which kind of defeats the purpose on, when I was making some of these pieces fit in a tighter area. The wider bend radius is it's gonna make that micro cracking less prominent, but it might not fit what you're trying to fabricate, and if it has to fit in a specific area.
Awesome. Another question we got on 5052 is, would you make a fuel tank or a gas tank out of 5052, or would you use a different alloy for something like that?
It kind of depends on the size. So like if I was making a motorcycle gas tank or something that I'm shaping to, kind of form and conform to the design of the bike, I would make that out of 3003 because 3003 is easy to hammer and bag it. Like if you've got your your bead bag and a mallet, and you can get it to a rough shape. Then you can put it in your plenishing hammer or even your English wheel. So 3003 is great for doing that stuff with. The 5052, not so much. You'll beat your arm out of socket if you're trying to form that into, into some sort of decent round shape. Whereas if I'm making a bigger tank that's going into a race car, I would make that out of 5052, absolutely, because it's got straighter edges. And if I'm not bending a lip in it, like if I don't have to bend a 90-degree lip into that gas tank, 5052 is great. Even if you're at 90 degrees, that's about the most I'm going if I'm using 5052. So, but I guess like anything where I want that extra strength, like I said, I put 4,500 pound cars on these aluminum stands we make, and they're only out of 1/8 inch material. So the 5052 is definitely high strength. It's great for fuel tanks, but again, if you're adding a lot of shape to your fuel tanks, the 3003 is going to give you a lot less headaches.
One other question we've gotten is, can you talk a little bit about 1000 series aluminum?
Yeah, so 1000, you're getting basically that's close to pure aluminum. And it's in the motorsports industry, don't use it that much. If you're going to be using 1000, it's going to be aluminum doesn't even get strong until you alloy it with other elements, right? So that's why 1000 series is basically considered pure. If you want to work with it, try and find something that's 1100. That's a little bit better. But really, even if you're doing like an aluminum panels, you're making aluminum panels. If you're making an aluminum door skins or aluminum fenders, things like that, that you need to add shape to, the 3003 will allow you to work it, but then it work hardens as you're working it. So it'll hold those shapes better when you're done working it. Whereas the 1000, it's going to be soft pretty much, the whole time. It doesn't work harden as well as 3003 does. So I stay away from the 1000 and 1100 series. I do use 1100 as a filler metal sometimes. And I'll use 1100 on 3003 if I need to join two panels of 3003 together and still need to hammer it or plenish it, because the 1100 series, which we'll go into some detail on picking out your filler metal here next, but the 1100 series filler metal is great for welding the 3003 to another 3003 panel and then being able to metal work it.
Another question we got that's kind of tangentially related to aluminum and definitely related to kind of the motorsports side of this is, how would you go about welding a magnesium engine case?
Well, magnesium. Yeah. So the question is, I don't know if you heard, are you talking that to the group
Yep,
then, James?
everyone can hear that.
Okay,
Yep.
great. So, yeah. So magnesium engine casings, or even old transmission cases, things like that. Magnesium welds similar to aluminum. It does have its own dedicated filler metals. It's lighter than aluminum, and in some cases even stronger. So it's very popular. We even use it sometimes in the motorsports industry. We'll make aluminum spoilers out of it for the race cars, or magnesium spoilers instead of aluminum ones, because it's lighter. And, most of the time the tech officials can't tell the difference between the magnesium or aluminum anyway. So we'll make magnesium ones when we can kind of get around some of those rules. So, but the aluminum is welded kind of the same way as you would on, or the magnesium is welded kind of the same way as you would on aluminum. You're using AC on your machine. So kind of those similar types of settings. The only difference really is going to be the filler metal. Another caution point, though, is when you're fabricating it and you're cutting it and you're grinding it, the dust and chips that you are creating from the saw cutting and grinding, they are flammable. So make sure that you scoop those things up and remove them. You don't want that stuff to pile up, because if you do start throwing sparks on a magnesium dust area, you'll have a mess.
One more question here. What are most aluminum trailers made from?
That'd be a good question. So depends on how they're making it. If they're making it out of like just aluminum tubing, some of it's extruded stuff, like aluminum I-beams. I would think that could be anything from 6061 to 6063 alloy. There's 5000 series extrusions. You're probably going to want to check with, if you have a specific manufacturer in mind, you might want to check with them. If you're doing a repair, they'll be able to tell you the alloy. And once you figure out the alloy, I will show you how to pick out the right filler metal. There is some apps that I can show you, but there's basically some filler metal properties that you'll go through and decide, do I want strength? Do I want crack resistance? Do I want temperature? Do I want post-weld heat treatability? Those types of things are all different properties, and you'll just determine the right filler metal based on your application. So off the top of my head, I wouldn't be able to tell you exactly what alloy it would be. We've made trailers, mostly the ones that we've done out of aluminum have been 6061. So, but I would think there's other alloys, especially the extruded stuff.
Yeah, I've definitely seen quite a few, especially like horse trailers and stuff like that are made out of the 5052.
Mm-hmm.
But yeah, I've seen 6061 as well. Another question that we've got here before we kind of move on is, can you ever come close to returning aluminum back to its original state? I know you talked a little bit about annealing it, but once you've welded it, can you get it back to that tempered state?
Certain alloys, yes, but most of the time the as welded condition will be no. So, for example, certain filler metals are not post-weld heat treatable. So if you're working with, let's say it's a billet cylinder head and you're welding this up, it's really not feasible on a one-off item unless you have a lot of the ability to do some high temperature controlled areas where you can put this thing in a temperature controlled oven at X amount of temperature for X amount of time, and then you're stepping it at down. It's not nearly as easy per se. Now, when you get into the alloys that aren't heat treatable, like anything in the 5000 series, the 3000 series, the only way you're going to return that to a higher temper is probably going to be like cold working it. So you can, anytime you're hammer forming it, you're adding more temper to it. If you're rolling it in your English wheel, you're cold working it. You will probably get that back up close to you might get it back close to like an H14. I don't think you'll get it back all the way up to an H34, but you probably get it up to an H14 just by cold working it.
Another question that we get quite a bit is, if I know what my base metal is and I know what my application is, how do I determine the right filler metal for that?
Great. Yeah, we'll be talking about that. I think that'd probably be a good point. We can probably jump into that right now. Is one of the things we like to talk about is the application, right? Picking the right filler metal for the application. So one of the things that a lot of people just jump into and guess about is, okay, well, my distributor has 4043 and 5356 filler metal. That's pretty much all he carries. Well, that's what he wants to sell you, but they can get it. They can get whatever you walk in and ask for, right? So if you have a specific application, it makes sense for you to decide which filler metal is best for that application. So when I do a lot of work in the motorsports industry, if anything's in the engine compartment area, I'm going to be using filler metal that is going to be rated at a higher temperature application. So filler metals that are rated for higher temperature applications, let's take a step back first. Does anybody know, if you've watched some of the other Shop Talk Lives, maybe the one that we did on filler metal selections, I think Galen did that one, they should have talked about temperature applications. A high temperature application for aluminum is really only anything above a sustained 150 degrees F. So that's really not that high. Anything in that engine compartment is going to be over 150 degrees. So right then and there, I know that that's probably going to be one of my primary things that I want the property of that filler metal is to be able to be operated, sustained in a high temperature application. So when I make these tanks, this is 3003, I'm using a 4043 or a 4943 filler metal because they're suited for high temperature applications. The 5000 series, even though they typically look nicer and give you a shinier weld puddle after you're done welding it, so they look good, it's not suited for a high temperature application. So a good example of this is like the turbo inlet charge tubes, right? A lot of those charge tubes, they're 6061. And I see people welding them with 53, 56 filler metal quite often, and they look beautiful. However, they're under pressure and they're in a high heat application. And they wonder why their welds are cracking. And it's because the 53, 56 material isn't suited for high temperature. And because the charge tube is thin, there's something that is called base metal dilution. And what base metal dilution is how much of the base metal, when you're welding it, is melting in with the filler metal. So it combines, and then it will change the properties of the filler metal to give it more, if it's temperature, if it's 60, 61, and you can get enough base metal diluted into the filler metal, you could get away with some of that little bit higher temperature applications. But the charge tubes aren't thick enough. Okay, so you're not going to, your weld bead is going to be mostly filler metal. So one of the things I want to show, or at least discuss, is picking the right filler metal. There's a couple easy ways. I know y'all got smartphones, right? So if you go and download, you see this little app here in the corner? That's the Hobart Weld app. If you hit that button and then sign your life away and hit acknowledge, I can pick the Hobart filler metal selector chart. Now that selector chart, if you're going to download it and just do it in paper form, looks like that. So here I've got the base metals, I've got the filler metal alloys, and then I also have the same base metals on the top. So if I want to pick, say, 6061, it's on this line, and I'm welding it to 6061, and then I follow that, meets down to that line right there. These are all my filler metal options, and they're the different properties. So these are the different selection properties up here, and I got a better viewpoint of that. When you do it on the app, okay, this is what you get. You don't have to muddle through that whole chart. When you go on the app and I hit my aluminum selector, yeah, trying to do this backwards and upside down. There we go. So here I've got alloys and alloy B, alloy A and alloy B. So I can just scroll through this and I can pick all these different alloys that exist, okay? And there is a lot of them. So let's just go back up to 6061. Let me find it here. 6061, and I'm welding to 6061. If you're only welding 6061 to itself, then you have to pick 6061 on both alloy A and alloy B. Okay, so I've done that. Then I'm going to hit view and that's the same chart that I printed off here. So now I have my filler metal properties. Okay, these are all the filler metal options that are recommended for welding 6061. So my properties are cracking, strength, ductility, corrosion, temperature, color, post-weld heat treat, and toughness. So what does that all mean, right? So cracking, it sounds self-explanatory, but it's really not. It's hot cracking during the welding. As the weld is cooling, certain filler metals have a tendency to crack, and that structure, that grain structure, will crack if you're over temperaturing, if you're putting just a little too much temperature on that filler metal. So anything with an A rating is great at resisting hot cracking. Strength, now that is self-explanatory. That's just basically the strength of the weld after the post-weld weldment area. So D obviously isn't as high a strength as A. A is going to be a lot higher strength, more closely mated to the parent metal strength. Ductility, these are going to be some of the areas that you're going to want to work with on filler metal if you still need your filler metal to be highly flexible, where let's say we're welding 3003 material and you need that ductility. Ductility is how much the weld will stretch before it fatigues. So you want that weld to be able, if the weld is too hard, the ductility will be less. And a lot of times, not always, but a lot of times if your strength is higher, your ductility will be a little bit lower. But with 6061 as being your base metal alloy, on this particular application, that is not true for 5183 filler metal. The strength and ductility are both A. So that is an excellent filler metal of choice if you need high strength and you need the weld puddle to still be, flexible. Corrosion, basically that's if you're in an environment where it needs to be resistant to both fresh or saltwater corrosion. Temperature, this is where we talked about being in a high temperature application, anything over 150 degrees F. Color match, now that's not the color of the weld puddle or the weld bead after you're welding it. That's going to be color matching if you're talking about doing any anodizing afterwards. And you want to make sure that the weld puddle, the weld bead is going to anodize at the same color or similar color as the original base metal. Okay. So if you look here, 4043 and 4943, they don't even, that box isn't even checked. There's not a letter high enough that will color match 4043 or 4943 to 6061. So it will not, if you're anodizing it and you use those two alloys or one of those two, it's going to be a completely different color at the weld puddle. Your weld bead is going to be completely different. Toughness kind of sounds like the same thing as strength, but it's not. Toughness is going to be a rating based on, let's see how the best way to say it. The plasticity of the weld bead, or some people call it plastic deformation, which means how far can the weld bead bend and shape before it actually breaks or pulled apart. So in other words, like this 6061 material, when I bent it, its plasticity was not very good, right? Because it didn't allow me to deform it where it got to the point where the strength was reduced, but yet the material still stayed together. That would be the toughness of the weld puddle. So again, that if you need your weld puddle, you're going to be hammering the weld puddle on a plenishing hammer, you're stretching it. You don't want to get to the point where it actually causes it to start cracking. So another example of that would be, let's talk about 3003. This is that 3003 material that is easy to form and it's easy to work with. But let's look at our filler metals. Here we talked about 1100. Somebody asked about 1100 earlier. So 1100 is going to be excellent for welding 3003 material if you're going to be metal finishing it and working it afterwards, because it has awesome ductility and it has excellent toughness. So basically you can beat the hell out of the weld puddle of the weld bead after you're done welding it and it'll still stay together. So, any questions on picking filler metals? I mean, we've got examples. I've got examples for even different filler metals for different, combinations. So if you look at This is going to be the widest one. This is going to be 3003 to 6061. Okay, so when I made these tanks, this is the exact scenario that I have right now. I got 3003 material and I got 6061 bungs and fittings. So on this particular case, I got my alloy A, alloy B, my filler metals of choice here. And because it's in an engine compartment and I really want that high temperature as my first filler metal property, these are going to be the ones that I'm going to be looking at. I'm going to be looking at the 4043, the 4145, or the 4943. Notice that nothing in the 5000 series alloys are compatible with that high temperature.
So we did get a couple of questions, Andy.
Yeah.
What's the scale of difference between an A rating and a C rating?
Oh, it's a lot. C would not be recommended. Yeah, I mean, it's the next lowest of, besides not even checking the box. So, for example, if you're looking for post-weld heat treating, 4943 can be post-weld heat treated, but 4043 can't. And the alloy, that's a very close alloy. They're almost in the same family. So the 4943 can, but the 4043 is not recommended, and it's a B. So that's A and B. C, if you're going down to a C rating, then C means you have to take into account some additional welding, not only parameters, but again, we're going to talk about that base metal dilution. If you can dilute enough of the base metal in with the filler metal, then a C rating would make it somewhat acceptable. I would recommend if you're going with something that is C rated, to call the manufacturer of the filler metal and tell them your application, and they could give you a better estimate of if you will have enough base metal dilution to the filler metal to give it that property. I hope that makes sense.
We got a couple of questions here on peening the weld after welding. So, you know, what about, I think this is specifically in relation to the info earlier about, you know, post weld kind of trying to get some of that strength back into the material.
Yeah, so it helps to add strength, but what it helps reduce stress risers in the weld too. So, you know, what we'll do on say if I'm welding a block, or you know, if I kick the rods out and I windowed the side of a block and I'm putting a big patch in the side of a block, I'm doing a lot of welding there, but at the same time I'm welding and then I'm stopping and I'm peening the weld as hard as I can, and I'm doing that as fast as I can to try and get that weld puddle as it's solidifying. It's gonna, you know, basically you're trying to improve the grain structure. You don't care what the weld's going to look like afterwards. That's not about looks at this point. It's about strength and getting the grain structure better with that aluminum. So, you know, you're trying to basically reduce the stress risers in that piece. So I've put Aries blocks back together multiple times, you know, but really the best way to just peen it is weld a little bit and start going at it with your hammer. I use actually a little rounded nose hammer on it, and so, you know, it's not a flat; it's rounded, so it does dent the weld bead. You know, it does not make it look nice, but that's what I'm doing, is trying to, you know, keep the stress risers out of the weld puddle.
If you wanted to harden a piece of aluminum by peening it or cold working it,
Yeah.
would you only peen metals that have decent ductility, or can you peen pretty much any heat treatable or cold workable?
Oh yeah, it doesn't matter. Cold working will make any of those harder. 6061 not so much, because it's already, you know, well, I don't know why you would anneal it anyway. 6061, it's just not a fabricating. It's not really a fabricating alloy for bending and forming. I guess you could do it. I don't know anybody that does it with 6061, but your 5000 series for sure. Yeah, and even literally just running it back and forth through your English wheel again will do it. But again, you're not going to get back up to those. Like I say, even if you're using say 3003, you can cold work 3003 probably back up to H14, which is going to be that 22K roughly for tinsel, and about 20 to, I don't think it's even 30, probably 20 to 25 on your hardness scale. So that's probably going to be about it when you're cold working it. If you're looking, I don't think you'll get it back up to say an H34 on 3003. H34 is on the high end is 40 on the hardness. So I don't think you can get it that high. If you do, you're probably risking deforming what you're fabricating. So there's got to be a balance there of what you're fabricating and then how much you're willing to cold work it to get the hardness up and still keep the shape that you want. So, I guess that's the tough point. In motorsports fabricating, and the fabricating that we're doing here, that hardness isn't really, we don't come across that as a primary fabricating factor. Everything we build, from expansion tanks to even these seats. Now when you look at these seats, I'm going to change you over to my other camera. You can see how much welding is done on this thing. There are so many linear inches of welding on this piece. You would think that the as welded condition would be so soft that you'd be able to bend this thing by hand, but it's not. This has not been, cold worked or anything to try and get strength. Basically, the shape of the seat with the additional gusseting, that is what gives this seat its strength. It's the design. It's not necessarily cold working it back from its bent shape.
Got one other question here before we move on. Is 4043 a tougher filler metal than 5556?
Is it tougher? It just depends on the application again. So if we go back to 6061 and we look at these, so 5356 does have it's tougher, but it's also in strength. It's a little stronger than 4043 and 4943. So yes, it is. But again, ask you if you're using it for strength. I'm going to give you an excellent example. I don't know if I can even turn my camera for it, but those wheel stands I talked about, those things have to be strong. I use 5356 filler metal on the 5052 fabricated pieces I made because I went strictly for strength. So if I'm understanding your question correctly, then yes, the 5356 is a tougher, stronger filler metal when used in ambient temperature applications. Yeah, that's a good question.
And that would be pretty similar. 5556 is going to be very similar.
Oh, 5556.
5356. It's just got a little bit more strength.
Yeah, and actually, the 5556 and the 5356, it has just a little. You're right. It has just a little bit more strength. However, the toughness is flipped.
Yeah.
On toughness, the 5556 is a little lower than the 5356. So, yeah. So strength and toughness, they sound like the same thing, but they're not. So in this, like if you're looking for resistance to deforming, that's toughness. How long? What's the farthest you can go before that severs its plasticity deformation? So 5356 is going to give you a better one there, but 5556 is actually a stronger weld bead.
Perfect.
Yeah, and again, please download that app because I used to have the chart on the glued to the side wall of my building by my welder, and man, my eyes would start hurting just looking at that thing, trying to figure out and meet the lines. And so the app has been a great help. So kudos to Hobart for putting that out.
Real quick, would you mind comparing that 5556 to 4043 or 4943? I think it's pretty much going to be the same kind of setup where you might get, you're going to have lower toughness and you're going to have lower strength as well with that 4043 or 4943 really, than, versus that 5556. That 5556 is always going to be, stronger and a little bit tougher than the 4943. In fact, if you're using 4043, we probably wouldn't recommend you use that if you have toughness as one of your key
oh yeah, no doubt.
applications.
Yeah, no doubt. And then again, I'm showing you this with alloy 6061. If you're using a different alloy, this might change a little bit, but in general, the 5000 series are going to have a higher manganese and magnesium content, so that's going to add strength. Unfortunately, it kills its temperature, right? So if you want the highest strength and still be able to maintain that high temperature, the 4943 is going to be your better option than the 4043, because in certain joint designs, the 4943 can be up to 30% stronger than the 4043, even though here on the chart it's only going from D to C. But yeah, so basically, if that makes sense, right? The 5000 series does have that higher manganese and magnesium content, which will give it some additional strength.
One other thing, is there any way you could show the elephant stands?
Yeah, actually, I got a car on it right now. Hold on, let me see. All right, so I didn't plan on moving cameras, so if you see something that you're not supposed to see, you didn't see it.
Doing it live.
All right, yeah, right? Who said we couldn't be, all right.
Boy.
Who said we couldn't do stuff on the fly?
Oh,
Can you see that?
Yeah.
Okay,
Looks
I
good.
can't tell. All right. You're gonna have to tell me if I'm back to where I'm supposed to be.
Close enough right there.
Is it?
Yeah, close enough. Maybe a little bit more to the right if you can.
My right or your right?
Oops. You're right.
Sorry.
Right there is perfect.
All right.
I think that covers all the questions that we had.
All right, so let's jump into, so we talked about filler metal. Let's talk about some of the welder settings, like where does frequency and balance fit in? I'm assuming most of us have some of the newer machines maybe, or at least if you're exploring some new machines, you may want to entertain machines that have the ability to change frequency and balance. Now, frequency controls the amount of the cycles that are in 1 second. So a standard frequency TIG machine is about 60 hertz, which is the power coming out of your wall is 60 hertz. It's 60 cycles per second. Now, on the inverter machines that we build, you can adjust that frequency because we make the AC artificially inside the machine. We're not magnetically coupled through a transformer to the line power. So that's the neat thing about inverters, is we can make it whatever we want. So when we're welding with AC, as you increase the frequency, the arc tends to be more focused. It gets sharper. So I can now fine tune my welding arc by changing the frequency. Now that's awesome when I'm working with, say, I want to fine tune, let's say, the outside corner of a weld joint. So now on this piece here, I welded this at a frequency that was low enough to tie in the two toes to the outside of this piece, but not high enough that the arc was so pinpointed that I had to literally move the torch back and forth. Okay, I want to be able to move the torch on a steady, you know, a steady travel speed along this piece. Now, a lot of people will turn that frequency up, but what they'll find is to get the weld puddle to widen out properly, they just put more power into their foot pedal, and now they're overpowering the aluminum, because what they're doing is they're just widening the puddle out to what they see is wide enough, but what they don't realize is they're punching through the backside. So now if I wanted to weld inside this included area, I would turn that frequency way up, because that pinpoints the arc and I can focus it all the way down inside this joint. Now, a lot of times with the lower frequency, you'll find that the arc wants to wander. It wants to go here and it wants to go here, wants to go here. It doesn't want to stay focused and go into the root of the joint. Increasing the frequency will allow you to get down into those areas and be a lot more precise. One of the things that I use that for is when I'm doing work on these. Okay, this is a big Brodix cylinder head. Now, I don't know if any of you guys are tackling stuff like this, but the concept is the same. You've already asked questions about blocks and transmission casings and things like that. So this holds true for this too, right? This is a casting. This is a Brodix casting. When you get into castings, most of the time it's going to be like an A356 alloy. So if you went on your Hobart selection app and you looked up A356, it would show you that the 4043 and the 4943 are going to be better filler metals for working on this type of an alloy. Okay, so really and truly, the best filler metal when working with A356 is have your dealer special order you A356 filler metal. They do make it. So that would be my choice if you can get that, because that'll be a better blend for this stuff. So the A356 casting. Now what you'll find here is, let's say you dropped a valve and the valve chewed up the deck of the head. Now you got to put a lot of welds here to, which you don't care what they look like, because you're going to surface that off anyway. So on this part, I run my frequency lower and put a wider, fatter bead. Okay, I'm not looking for deep penetration. I'm just looking to fill those nicks and all those areas that I took my carbide cutter and I ground them out, and I'm just filling up all them nicks, right? But when I get into the cylinder area where my valve seats are, or when I'm going around bolt or stud holes, I'm going to want that precision, because what happens when your arc is wider, because your frequency is lower, when you get closer to these edges, it sucks the aluminum in, and then you have to over weld it. And then what do you do the rest of the day? You grind it back out. So wouldn't it make sense if you could just do all your deck work at a lower frequency, and then when you get right towards the edge of the combustion chamber or down in by the valve seat area, you stop, you go to your welding machine, you turn the frequency up, and then you put a real nice finish bead around these edges. Now, like you can see, I might want to turn this other camera on, you might be able to see it better. You see this here? This is a real small weld bead right around this combustion chamber. Now, it looks like, like, oh, it's just sitting on there. No, it's not. When you increase the frequency, it tightens the arc up, but the other effect it gives is it gives deeper penetration. So it forces the weld puddle into the base metal deeper. When that weld puddle is narrower, the frequency is driving it in deeper. So now I can make some of these adjustments and literally put some finish welds right where I need to, and I don't have to spend the rest of the day grinding and reshaping those chambers. So frequency focuses. That's all you need to know. The higher the number, the tighter the arc. Lower the number, lazier the arc. Now, balance control. Balance control is another feature that you can adjust. And what balance does is it helps the cleaning of the aluminum. So when I say cleaning, I'm not talking about removing grease, oil, dirt, and all that. That you have to do yourself. The machine can help clean the oxide layer off the aluminum. So aluminum, it's nice and shiny. Well, what you're seeing is the oxide layer. The oxide layer is shiny. What's underneath, the raw aluminum, not so shiny. So if you brush it, you can see the difference between the piece of aluminum that is not been brushed and the piece that I brushed. So the aluminum underneath it is actually dull. So the oxide layer is shiny and that's really super hard. Aluminum, depending upon the alloy, it melts between 1400 and 1600 degrees. But the oxide layer that forms on the aluminum, 3700 degrees, right? So you have to chip that oxide layer off. So that's why we use AC, or alternating current. And if you were on one of the beginner ones, Andrew probably discussed the effects of alternating current on aluminum. So the positive side of the AC helps chip those oxides off. The negative side of the AC does the welding. That's where the heat goes into the piece. Balance can control those times so that I can adjust the positive side of the AC and the negative side of the AC. And what that does is it changes that etching zone on the aluminum. That etching zone is that white area next to the weld puddle. And you basically need to see a little bit of that white on that weld puddle so that you know you've cleaned enough. So you see just on the edge of this weld bead, this puddle here, I've got just a little bit of that white area. Now, a lot of people, I'll see if I, like on this piece here, that's not even a good example. I have some pieces. Oh, let's do this expansion tank. Okay, this is a good example. This is an example of an expansion tank. You can barely see the etching zone. It's almost non-existent. And what happens is you will start seeing some speckling inside the weld bead. Now, if I was inspecting this piece, I would fail it because there's not enough cleaning of the oxides on some of these joints. And I can literally see with my eye that there is some speckling, there's contamination in some of the weld beads. So that would have been an area where I would want to lower that balance number. Lowering the balance number takes energy away from the negative side and puts it on the positive side so you can clean those oxides off better. Okay. Now, you can change that by joint design. And the reason I adjust my balance is because if the metal is falling away from your tungsten, okay, so you're welding this in this configuration. Now, the base metal is falling away from the tungsten, which means the AC isn't going to be as effective on cleaning this piece because the base metal is farther away from the tungsten. So I need to lower my balance when I'm doing an outside corner. Now, inversely, that's not true. If I'm welding inside here, now the base metal is closer to the tungsten, so I can increase my balance and spend more of my time in the weld portion of the AC. So in this case, I would set my balance up to maybe 80%. On this side here, I'd have it down to around 71, 72, something in that area. But the idea is make sure you do see a little bit of that etching. That way you're going to make sure that the cleaning is proper so that the edges of the weld, which is called the toes of the weld properly fuse to the base metal. Okay, so we're running a little bit low on time. Any other questions on frequency and balance?
We did get a couple questions just on basic tungsten prep. With inverter machines, what types of tungsten should we be using, and how should we be sharpening that tungsten?
Okay, so yeah, so the question was on sharpening tungstens, and so on the inverter machines. On the inverter machines, I typically use a seriated tungsten. I like the all-purpose tungsten, so I like to be able to go from steel to aluminum or aluminum right to steel using the same tungsten. The only thing I do when I do that is I pull the tungsten out and redress it. Now I'm gonna leave you for a second. I use a dedicated tungsten sharpener, which I should have had out here. Well, it's plugged in under my bench. You're not going to get to see it. Sorry, but I use a dedicated tungsten grinder. It's a handheld version. It has a diamond grit, fine grit wheel on it, and that's what I use to grind my tungstens. Now it has a block on the top of it that is machined for different size tungstens and different angles of your tungsten. So I like a 30-degree grind for most stuff. Um, that's another misconception I think a lot of people have is when you're talking about the grind angles. I'm going to draw you something out here. I didn't even get to do any welding today. This is not good. So if this is my tungsten, your grind angle, and they probably talked about this on one of the beginner ones too. Your grind angle is going to determine how the arc flares off the tip of the tungsten. So a lot of people think that if I put a long taper on my tungsten, that it's going to be more pinpointed, and that's not correct. Okay? If you put a longer taper on here, the arc tends to start to jump off the tungsten roughly at a 90 degree to the grind. So you're actually making your weld puddle wider. And so I grind at roughly a 30-degree grind for most of my stuff. For aluminum, you still grind it to a point on the inverters. You can take it and just knock that point off, just snub it off a little bit. If you don't do that, it's not a big deal. The amperage that you are using on your machine will cause that point to just pull up a little bit. So it may form a real tiny ball on the end of it. But I like using the seriated because it's an all-purpose tungsten. I can run it on AC and DC. If you primarily use AC, you could also use lanthanated, but it has higher performance than, say, a green tungsten, which is pure tungsten. We don't recommend putting pure tungstens in the inverters at all. They can't handle the advanced sine waves that we're putting out on the machine. Think of pure tungsten like pure aluminum. It's kind of useless until you alloy it with other elements to make it stronger. So tungsten, like seriated tungsten, it's doped with the rare earth element cerium. Lanthanum for lanthanated, right? So you can get into these different blends of tungstens also. There's some companies that make like trimix ones where they have 3 different elements on it. But for most of what I do, the seriated tungsten works the best because I'm constantly switching from welding high strength, low alloy steel roll cages, and then I'm welding aluminum next. So I like that versatility of the seriated tungsten. But if you primarily work with aluminum, try the lanthanated, you'll like it.
Perfect. One last question here before we wrap up.
Yeah.
When would you use hammer peening, like in an application? Like, would you use that on an engine head, or where might you use that?
I don't typically use hammer peening on a head. I use it if I'm blowing out sides of blocks or those thick areas where the block or the webbing. If you're doing lots of welding. So, I might be welding in a piece of 1/2 inch thick or even thicker aluminum, making a patch. And I've got that patch and the block, I've got it beveled. So the point where it's not an open root, but it still sits in there fairly tight, but I'm putting a lot of weld bead. Those are going to be the areas where I'm going to be peening. Now, if you're talking like plenishing, then that's a different story. That's working with like the softer aluminum, and I'm plenishing out a lot of the dents that I'm making if I'm hammer forming a piece, and then I want to smooth those out with the plenishing hammer. You know, I think you're talking about peening though with just a round nose hammer.
Yeah, to kind of try and increase strength a little bit.
Yes, yeah, exactly. Yeah, that'd be it. But great.
All right, I think we've kind of covered all the questions that we've got here tonight. Want to thank everybody for joining us here on the last episode of Shop Talk Live Aluminum Series. Again, just to let you guys know, we will be taking a break from Shop Talk Live for the summer, but we'll be back later this year with some more episodes. Again, thanks everybody for joining. Andy?
Thank you, James. And yeah, if you have any suggestions on other topics you want to see Shop Talk Live address, definitely email those to us. We always love your input.